Welcome to lesson 10.1. We are diving right into unit 10 with beginning graphing exponential and logarithmic functions. We'll say log functions for short. The beginning of this lesson, though, we will focus primarily on exponential functions. So when we are looking at exponential functions, what we're doing, let me go back to the right file. What we are doing is looking at functions that look like this format. Some function, we'll call it f of x. You could say g of x, h of x, just the name of our function. So we will have numbers raised to a certain power where that a value is called the base. So some number raised to an x value. Now, you are going to notice that what we can easily do is randomly choose any value and start raising it to the power and plot certain numbers. But I'm going to have you guys focus on certain critical points. And so up here in your upper right-hand corner, I want you guys to focus on the critical points that have the following structure, okay? And this is going for exponential graphs. You are going to have 3 points that I would require you guys to draw, at least. The first one would be -1, comma, 1 over your a value. Now remember, your a value comes from this right here, the base of your exponential function. The second point I would have you plot is 0, 1. And the third, 1, your a value. So let's show you how this will be done with the first example that you see right here. So we have y equals 2 to the x power. So here's our function, y equals to the 2x power. So the first thing I want you to do is to identify what your a value is. In this case, our a value is a 2. Then you are going to construct your x and y table. Okay, here's your x and y table with the values of the critical points that I asked you to do earlier. Notice that your x values are going to be -1, 0, and 1 as highlighted there. So I'm just going to bring what I suggested there, -1, 0, and 1, and put them in my x column. To evaluate the y column, I am merely going to substitute these x values right into here, which is the exponent, 2 to the power of x, and evaluate and put it for y. Now, if I know the pattern of my my critical points, the answers will always be 1 over a, 1, and a. Okay, so let me show you what that means. So if I plug in a into, If I plug in the -1 into my function, it's going to be y equals 2 to the -1 power. So I'm going to write this down here temporarily, y equals 2 to the -1, because I'm replacing the x with the -1. 2 to the -1 power translates as 1 over 2. That's one of our exponential properties. But if you look up here upstairs, I told you that your first point, your first y value that goes with the x, -1, is always going to be 1 over a. So 1 over a is indeed 1/2, 1 over 2. Then if I plug in for the next row, y equals 2 to the 0, well, 2 to the 0, anything to the 0 power is going to be a 1. But again, look upstairs, the green up here, that is exactly what I told you it would be, a 1. The last one, y equals 2 to the power of x, in this case is 1. Well, 2 to the 1 power is just a 2. Isn't that our a value? That's what I told you that the critical point would be. So you do not have to substitute and evaluate if you memorize the pattern of your critical points up here, upstairs. Notice that I am merely substituting my 1 over a, my 1, and my a. So I'm going to erase these as how we just did it. My first one, -1, recall, needs me to put the 1 over the a value. Well, the 1 over my a value, well, my a value is 2, so I'll just put 2. The next one says to just write the 1. There's my 1. And the next one says just write the 2. Write the 2. Okay? So it is plugging in to your equation, but you just memorize the pattern. So let's go ahead and plot these numbers. -1 comma half. -1 comma 1/2 would be, I'm going to stretch this up a little bit, is going to be right here. So -1 1/2. The next one's going to be 0 comma 1. 0 comma 1 will be right here. And then the next one is 1 comma 2. Now you'll notice that this is not really a straight line, okay? So don't be tempted to connect the dots like a straight line. Exponentials grow exponentially. There's a curve that is occurring, okay? Well, there's a certain asymptote that I need you guys to always remember that comes with exponentials. Exponential functions have a horizontal asymptote that occurs at the x-axis, but we write the equation y equals 0. So I'm going to put HA for horizontal asymptote, and the horizontal asymptote is y equals 0, okay? So when you're drawing your curve, I want you guys to recognize that this curve will get asymptotically close to this horizontal asymptote, but it doesn't ever touch. And then obviously it exponentially increases. Okay? So please, please, please remember that every exponential function has an asymptote of y equals 0 unless some sort of translation occurs, okay? Now, in addition to remembering that feature, I want you to also recognize that your exponential function has a y-intercept occurring at 0 comma 1, which you'll see is one of our critical points up here. Okay, the 0 comma 1 is my y-intercept. Next, I want you to recognize that when an a value, your base is given, if your a value is bigger than 0, then, or it's a bigger number, well, not bigger than 0, my apologies, bigger than 1, then your function, your exponential function, is going to increase. Okay, as shown in this specific problem. Okay, so let us proceed to do the next one. Okay, y equals 1/3 to the x power. So let's scroll over here. I'm going to make an xy table again, and I'm going to evaluate at -1, 0, and 1. And I know that my first value has to be a 1 over a, right? So 1 over a means that I need to go find what my a value is. My a value here is a 1/3. So 1 over 1/3, 1 over my a value, that just means take the reciprocal of 1/3. 1 divided by 1/3 means take the reciprocal of 1/3. That answer is going to be a 3. Okay. Now, if you're wondering how exactly does that work mathematically, well, I'll show you what that means. 1 divided by 1/3, or 1 over 1/3, is the same thing as you saying 1 times the reciprocal of 1/3, which is 3 over 1. And 1 times 3 over 1, well, 3 over 1 is just 3. 1 times 3 over 1 is 3. Okay? So it's that keep, change, flip that I think grade school teachers like to call it. Okay? The next one was just a 1 based on our critical points. So dragging downstairs again, see my green one. And then the last one is write the a value. So here is 1/3. So let's plot these points. -1 comma 3. So -1 comma 3 is going to happen right here. Let's see, it's not plotting. There you go. 0, 1, and 1, 1/3, which is really close here. We're not going to forget that we do have a horizontal asymptote at y equals 0. So let us go ahead and draw that horizontal asymptote. Okay. And we're going to label it. I'm doing yellow this time. So horizontal asymptote at y, that's not, let me erase some marks here, at y equals 0. And I am going to go ahead and connect my dots. So my exponential function is this time decreasing towards my asymptote, but again, it flattens out and it's so incrementally, infinitely small, you can't see how it's closely approaching the y equals 0 line, but it never touches. Okay, I do want you to notice too that the y-intercept is still at y equals 1, so your y-intercept hasn't changed yet. It's still at 0, 1. Y-intercept is the point where the line crosses the y-axis. Now, in this situation though, I want you to notice that your a value this time is a number between 0 and 1. So when your a value is between 0 and 1, then your exponential function is going to decrease. And I did not spell decrease correct. Okay, so our a value here was the number 1/3, which is 0.3 repeating. It is definitely falling between the 0 and 1 range, so our function decreases. So if you read your graph for this problem, number 2, from left to right, our y values are indeed increasing versus the one we just finished to the left where the y values are increasing. Now, one thing I do want you guys to recognize is that our graphs are sometimes going to undergo some transformations. And what I mean by transformations is that your graph is going to shift either left or right or up or down. So you have to keep that in mind, okay? So here is what you are going to notice in the next problem. We have y equals 3 to the x minus 2 plus 1. So the first thing we want to do is look to see if we can find the parent function of this entire function, okay? The original basic problem before all the transformations occurred. So what I mean by that, and I'm going to use my highlighter here again, is I want you to find the y equals a to x portion of this entire problem. So right now our problem reads y equals 3 to the x minus 2 plus 1. What is the a to the x problem? So what I'm looking to focus on right now is only this piece. Everything else that I am highlighting in green needs to be ignored for now, okay? So all I want you to do is focus on the yellow. So when you focus on the yellow, we can create a table with our critical points, and then we will move those points based on the transformations that we're seeing. So -1, 0, and 1. For some reason, it doesn't want to write. Okay. Let me try something here. I think my thing is freezing. Stand by. Okay. -1, 0, and 1. The first number is 1 over a. Well, we already established here by looking in the yellow that our a is 3. So we're going to write 1/3. This one's always a 1. And then the y-coordinate that goes with 1 is always your a value, which in our case is a 3. So -1, 0, 1 are paired up with y values 1/3, 1, and 3. So we're going to go plot those points, okay? So let's plot those points in black. So -1, 1/3, will be about right here. Make them big enough so we can see. Let's try that again. -1, 1/3. Then we have 0, 1, and 1, 3. So you're going to notice that this graph, again, looks just like what we've been doing. Okay. Recall that we know that there is a y equals 0 horizontal asymptote. So when I'm drawing this graph, I'm keeping that in mind. Okay, so this is the graph of y equals 3 to the x. So keep that in mind, because our goal is not to graph this one, but we're going to use this graph of y equals 3 to the x to help us graph the transformed graph. Okay, so what is the transformed graph? So the green portion has some additional numbers, and those additional numbers are causing the graph to move or to be transformed. Anytime you see a number that is adding or subtracting to the x, okay, so in this case, let me get out of the screen. So in this case, notice this -2 is affecting the x, okay? So this -2 is subtracting from the x. Anything that adds or subtracts from the x has to do with horizontal translation, okay? Horizontal translation. So I'm going to put horizontal. And what you are going to do is you're always going to do the opposite of what that horizontal translation is. So the -2 actually implies that my graph went to the right 2 units. Okay, so that's the first step you guys always do. You check to see if there's any horizontal translation. The second step, you check to see if there's anything multiplying, anything that's multiplying against your parent function. In this case, we don't have anything multiplying, so we move on. Now, what do I mean by multiplying? That means that right here in front of the 3, I may have put like a number 5. So it may have looked like something like this. 5 times 3 to the x minus 2 plus 1. That's what it would have looked like if there was a multiplication, okay? So in this case, nope, there isn't any multiplication going on. The third, you ask yourself, okay, well, is there any reflection going on? And it has to be in this order, by the way. You always have to check stuff in this order. Well, reflection, there is none, okay? Because there are no negatives being multiplied, okay? Negatives as well would appear right here in the front. You would have seen a minus in front of that base, and there are none. So there's no reflection over the x-axis. And then and by the way, step number 2, if there is multiplication going on, that's called there is a vertical stretch. So there's no vertical stretch happening. So just in case you were wondering what was the verbiage you will have to use, is vertical stretch. Number 4 is there any vertical translation? Vertical translation has to do with addition and subtraction of numbers. In this case, we do have, and you actually do exactly what the number says. There is vertical translation occurring, and in this case, it forces your graph to go up 1 unit. So with vertical translation, you do as it says. Horizontal translation, I want you to always do the opposite, okay? Always do the opposite of what is being asked. Okay, so that means we have to do 2 things. We have to horizontally translate right 2 units and vertically translate up 1 unit. So I am going to move those 2 values based on what I just found out. So if I move my first dot 2 units to the right and 1 unit. That means it's going to move this way, 2 units, and then up 1 unit. So I'm going to put that dot right here. And I'm going to do that for every single one of these dots. My second dot to the right 2, up 1 unit. And then this one I'm going to go to the right 2, up 1 unit. But I want you to realize now that what happened is that your horizontal asymptote also is being forced to move. Your horizontal asymptote that was y equals 0 has now moved up 1 unit and is now located at the y equals 1 line. Okay, your horizontal asymptote is now at y equals 1. So your graph now is still very close to the asymptote, but now has moved from the black graph to the pink graph. So this graph, y equals 3x minus 2 plus 1, is the graph that we were looking to graph. Hope that makes sense so far. Okay. Now, we will not worry about this graph, so don't worry about this. Okay. Let us move on to the next function. This was our log function. This was our exponential function. We're going to move on to log function. So flip over your page. And now I want you to realize what happens with log functions, okay? Now, on this graph, I want you to see how this equation right here, y equals log base 2 of x, is related to y equals 2 to the x. Now you bear in mind that y equals 2 to the x was the first graph that we graphed right up here upstairs, okay? So y equals 2 to the x, what I want us to do is to take these 3 points, -1, 1/2, 0, 1, and 1 over 2. And yes, I want you to just replot it over here on this graph, okay? So -1, 1/2, 0, 1, and 1, 2. And I want you to go ahead and connect the dots and draw the curve. Okay. Now, why am I asking you to do this? Again, I'm trying to show you what is the relationship of exponential graphs to logarithmic functions. So here is the relationship. So I want us to construct a line, and I want this line to have a slope of 1 and that it goes through the 0, 0 origin. So if I construct a line with a slope of 1, that means that the line goes up 1 over 1. And I don't have a ruler, so I'm doing my very best here to construct a line. So notice that your line will go from corner to corner. If you have a ruler, that would make it so much easier. This line here has a y-intercept at 0, and it goes up 1 over 1. And so it's called the y equals x line. Okay, the y-intercept is 0, the slope is 1. Now, if you were to take this pink graph and I were to ask you to reflect this graph from here over to this side, okay, that causes the graph to flip over the green axis. Again, you're taking this graph, pink one, and you're flipping over to this side, and then what's going to happen is that you are going to cause this graph to be imprinted on the other side, okay? Now, how is that going to happen? Well, what happens when you reflect over the y equals x line, so I'm going to want you to put a little note here, and that you are reflecting your pink graph, reflecting the pink graph over the y equals x line. What you're going to end up doing is you are changing your y's for your x's and your x's for your y's. So instead of negative 1, 1/2, you're actually going 1/2, comma, negative 1. So 1/2 to the right and negative 1 down. Instead of 0, 1, you're doing 1, 0. Instead of 1, 2, you're doing 2, 1. Instead of you having a horizontal asymptote at y equals 0, what you're going to end up having is a vertical asymptote at x equals 0. And so here, I'm getting ready to draw the vertical asymptote. So I'm writing this down. Vertical asymptote, x equals to 0. And so notice what's going to happen, okay? Our graph, instead of approaching the horizontal asymptote, now is approaching the vertical asymptote. Really, really, really close. And increasing on this side. And so do you see how that pink graph reflects over the green, over to become the green? The green graph is our log base 2 of x function. So here, I want you to know how to read this. Let's see, this is red. Oh, it's not letting me write in the margin, so let me do it on this side. Read as, let's go up a little higher here. Read as log base 2 of x. So what you just graphed was log base 2 of x. Now, fear not, I do not need you to always graph the exponential function to then be able to graph the log function. What I need you to do is recognize that since you're reflecting over the y equals x line, all you are doing is interchanging your x and y values. So therefore, the critical points that you are using for your for your exponential function are merely going to require you flipping them, okay? So again, you're going to have 3 points. But instead of your negative 1, 0, 1 being in the x, it's going to be in the y. And instead of your 1 over a, 1, and a being in the y, it's going to be your x. 1 over a, 1, your a. So let us test out this theory here, okay? Let's pretend I never did that reflection upstairs, and I'm going to construct the xy table for this log function. Well, this subscript is going to be your base. Anytime you're looking for a, that's your base. Base a is 2. It's always going to be the subscript in log functions, okay? In exponential functions, it's the exponent. In log functions, it's the subscript. So we know negative 1, 0, 1 goes on this side. We know that 1 over a, so that's going to be 1 over 2. This is the 1, and this is the a. So if I go look upstairs, 1/2 comma negative 1, well, 1/2 comma negative 1 indeed is this pink dot I'm drawing now. 1 comma 0 is this pink dot, and a 2 comma 1, whoops, I put a. I meant 2. And the 2 comma 1 is indeed this dot that we did. So that's how you will graph it, okay? What I need you to now remember is that the log functions now have vertical asymptotes, okay? They have vertical asymptotes at x equals 0. Instead of y-intercepts, they have x-intercepts. So the x-intercept is instead going to be 1 comma 0 versus the 0 comma 1 we're doing for exponential functions. Always remember that logarithms have vertical asymptotes. That's how I always remember, try to get my students to remember. Logarithms, the L for logarithm, gives us the hint that our asymptotes have to be long up and down lines, okay? So keep that in mind. So let's practice what we just learned with this example here on the right. We have log base 3 of x minus 1 plus 2. Log base 3 of x minus 1 plus 2. So what's the first thing we need to do? We need to find the base. That's the first thing we need to do. So our base is right here. It's the 3. Base is the 3. So let's go ahead and construct our x and y table. Now, remember the x and y table is always constructed for the parent function. The parent function only cares about this piece. We don't worry about any other number. We are graphing log base 3 of x. That's it. The minus 1 and plus 2 are our transformations. So let's fill out our table. Negative 1, 0, 1 goes on the right-hand side. My x is 1 over a. 1 over 3 is going to be this case. This one's always a 1, and then this one's always my a. And so 1/3, negative 1, 1, 0, and 3, 1 are the plotted points that I'm going to plot. So I'm going to come up here, and I need to graph 1/3, negative 1. So 1/3, negative 1, 1, 0, and 3, 1. Okay, so this right now is my initial graph. Now I'm not going to draw, like right now, just to draw the curve, it will disappear. But right now, this is my curve. This is the curve right now. Okay, but that curve has to move based on the transformation. So I'm not going to draw that curve right now. What I want us to do is move that graph. So we know that something is happening right here and right here. Okay, the first thing you ask yourself is, do I have any horizontal transformations? Well, we do know that we have a horizontal transformation of moving to the right 1 unit. Okay, because we do the opposite of what that minus, of what that minus tells us to do. Minus 1, do the opposite, so that's right unit. I'm writing in the margin again. Hold on again. So this means right 1 unit. Okay. And then we don't have any multiplication. There's no multiplication occurring right here. There's no number in front of log. And then reflection, also, there's no negative right here in front of the log. And vertical translation, that pertains to the positive 2. So positive 2 tells us that we have to go up 1 unit. Okay, so what does that tell us to do? Move those orange dots, right 1 unit, up 1 unit. So right 1 unit, so I'm going to move it right 1 unit, up 1 unit. Now I'm going to place it right here. And then right 1 unit, up 1 unit for the second dot. And then right 1 unit, right 1 unit, up 1 unit, third dot. Now my vertical asymptote is changing from the x equals 0, and now it's becoming, let's pick another color here, x equals 1, because it moved. Okay, so it's no longer that y-axis, it's shifted over. So now I can connect those 3 dots. Those 3 dots are going to go like this, and it's going to, let's try that again. It's going to go like this and get really, really super close. And it goes on to the right, increasing. So there's my log graph. Okay. Now I want to show you something that some people do like to do. Instead of using the graph, they just want to figure out what the values of the table are and then plot the points. So assuming that you understood where these numbers came from, okay, I want to show you what you can do using your transformations. So the first transformation said that we had to move right 1 unit. So what does that do to this table? If I go to the right 1 unit on this table, will that affect my x values or my y values? Well, let's draw them out. If I'm going right, that has to affect the x values. So my y values, nothing's happening to them, so I'm going to just write them down. But going right means my x values go up. So I'm going to add 1 to each one of these, okay? And so here this becomes 1 1/3. 1 plus 1 becomes a 2, and 1 plus 3 becomes a 4. But then notice that, let's pick a different color here. Let's do gold. Let's see what gold looks like. Then something went on another transformation, but this time it went up 1. Now up 1 does what to my graph? Up 1 affects my y-axis, right? My y-coordinates, not my y-axis. So that's why I'm going to bring over the x values because nothing's happening there. And up 1 means that my y values increased by 1. So I'm going to put +1 on each one of these and figure out what the answer to that is. So -1 plus 1 is 0. 0 plus 1 is 1. And 1 plus 1 is 2. And so now that I'm done with my transformations, I want you to notice what happened, okay? So look at these answers, and I'm going to use red to graph what we just found in our table to make a point. 1 comma 1/3, if I go from 0 and I go to the right 1 1/3 comma 0, that is indeed this red dot that I'm drawing right now. 2 comma 1 means go to the right 2 up 1, that is this dot I'm drawing over the green dot. And 4 comma 2, 4 to the right up 2 is indeed this dot. So you can do it that way as well, okay? And then just graph it in one shot if you like making the tables and figuring out where they go right off the bat, okay? So just know that that's an option if you want to do that. Let me see over here. Yeah, this one. Oh yeah, this one we did not do. So we will X out of that. Let's go over to the next sheet that you guys got. This sheet over here. Okay. So this sheet is going to be a homework sheet. I am not collecting it for a grade. But I do need you guys to complete it for practice. So I did want to draw your attention to a couple of the problems here. So it does not confuse you. Look at problem number 2, okay? Problem number 2 gives us a logarithm, y equals log x, but you'll notice, you probably are asking yourselves, well, wait, I don't see a subscript. Now, when that happens, when you don't see a subscript and it's blank, I need you to know that that blank subscript is implied, subscript, implies it to be the number 10. So if you do not see it, your base is 10. So here you have your -1, 0, 1. So they wanted you to fill this in. So that's why you see that they're writing the 1 over the a value is a 10. This one's always 1, and your a value always goes there. That's why they're writing in the 10. So I wanted to make sure you understood. If you don't see a subscript, don't think it's a mistake. Your blank subscript is implied to be a 10. Just like if I wrote 2 to the x plus 4, and I asked you what is the exponent of x, and you would tell me it's a 1. It's understood to be a 1 even though I don't write it in. That's the same idea, okay? So let's plot this. 1/10 comma -1. Well, 1/10 is a very, very small number. So 1/10 comma -1 will be somewhere around right here. 1 comma 0 would be right here, and 10 comma 1 would be right here. And remember, you have an x equals 0 vertical asymptote. So vertical asymptote is x equals 0. And so my graph connects these 3 dots. It goes really close, and it comes over like this. Okay? That's, remember, vertical asymptotes are for logarithms. See the letter L in log? Remember, it's long. So it has a vertical asymptote that is up and down, okay? So what are you going to do after you graph this one? Well, you work vertically down, okay? Don't work them out in order of 1, 2, 3, 4, 5, 6. So 2, go to 4. 4 tells us to take the log function, take this log function, and a transformation happens. Well, we already have the log function drawn here in number 2, but what is it asking us to do? It's asking us to go down 4. So every dot that you drew upstairs, you're going to go down 4. So I was subtracting my y values by 4. So if I'm right here, I'm going to go down 4. 1, 2, 3, 4. I'm going to be a little bit lower here. It runs out of the graph. And then I'm going to take this one and go down 4. 1, 2, 3, 4. And then I'm going to take the 10 comma 1 and go down 4. 1, 2, 3, 4. And here's my new graph. So it goes this way, that way. And then looking at the next one, it tells us to look at the log graph and what is happening. Well, this time my number is adding to the x. And recall that I told you that whenever you adding, okay, so what does this imply? You do the opposite. Opposite means you are going to add to, meaning go left 2 units. Okay, so go back to problem number 2, the first one, and those dots go left 2 units. So the original dot's right here, and it's going to go left 2 units. So 1, 2, so it ends right here. And then the other dot was right here at 1 comma 0, but it's going to go left 2 units, 1, 2, so it's going to go right here. And the next dot is going to be at 10 comma 1, and it goes left 2 units, so it goes right here. And notice this time, though, our vertical asymptote has to move. My vertical asymptote was at x equals 0. Now it moves to x equals -2, my vertical asymptote. And so my dots are curving downwards this way, and there's the graph. So this is basically what I need you to do as you talk yourself through these problems and practice graphing with your transformations, okay? And so here you will have a reflection. That's a reflection. So if you're wondering, how does my reflection work? Well, that means my original graph, let me write down the values of my original graph, x and y, okay? You had your -1, 0, and your 1. This was 1/10, 1, and 10. What happens is your y values change. Negate means multiply your y values by -1. That's what it means. So if I multiply this by -1, and multiply this by -1, and I multiply this by -1, I'm going to get 1, 0, and -1. So now those are my coordinates. My coordinates are going to be, let's write them over in green. They're no longer 1/10 negative, but with 1/10 1, 1 comma 0, and 10 comma -1. So let's do that. 1/10 comma 1 will go here, 1 comma 0, and 10 comma -1. And so the graph is going like this. Okay. And the vertical asymptote is still right here. Notice your vertical asymptote only changes left and right when the graph has horizontal movement. Okay. Last but not least, scrolling down to the next page, there's another value that you will see of a blank subscript. Okay. When you have a blank subscript with ln, ln means natural log. And you're going to learn a lot more about these in coming sections, okay? This time, your subscript is going to be e. E is the value 2.72 approximately. It's an irrational number, just like pi. You know how you guys know that pi is equal to, approximately equal to, let's say that. Pi is approximately equals to 3.14. And you know it's an irrational number. Well, E is a number, another example of an irrational. So when you see that, please know that it is merely a decimal value of 2.7 approximation. So when I'm asking you to 1 over E, 1 over 1 and E, I'm still having you use the Y values -1, 0, and 1. Okay. 1 over E, if you put that in the calculator, I forget what number that is. Hold on, let me write that down. It is approximately 0.37. And then again, this one's approximately 2.72. So 0.37 -1 is going to be around right here. 1, 0, and 2.72, 1. So here is the beginning parent function that you would use to help you graph the following problems in that column, okay, going downwards. Your vertical asymptote is x equals 0. That's not very straight, but you get my point, especially because I'm going to write the equation right there. Okay, so practice these and make sure that you understand how to do your vertical transformations, your horizontal transformations, reflections, and then head over to your delta math, okay? By the way, here on number 7, that's an example there of vertical stretch by a factor of 3, okay? So by the way, when you see a vertical stretch by a factor of any number, by a factor of 3, all that means is that you need to multiply your y values on the chart that you create. Okay, so when you end up drawing your x and y chart from problem number 1 up here, okay, these numbers right here, I need you to take these numbers right here and you're going to multiply them by 3, and that will help you generate the values of the points for you to plot. Good luck, and thanks for watching this very long lesson, but hope this has clarified how you use the basics to graph exponential and log functions. Remember, log functions are the inverses of exponential functions. They are reflection over the y equals x line.